NEC section 250.66 requires the grounding electrode conductor, often abbreviated as GEC, to be sized based on the largest ungrounded service conductor. This means the size of the wire connecting your grounding electrode, like a ground rod or concrete encased electrode, to your service equipment depends on the size of the main wires feeding power into your building. Consider a situation involving a spec home, which is a house built without a specific buyer in mind. Initially, this spec home might have a service panel rated for, say, 200 amps, and the grounding electrode conductor would be sized accordingly. However, after the house is sold, the new owners decide to add several high-demand appliances or systems like a large electric vehicle charging station, a swimming pool heater, or a significant expansion to the living space requiring additional electrical circuits. These upgrades collectively increase the overall electrical load of the house, necessitating an upgrade to a 400 amp service panel. The original grounding electrode conductor, which was appropriately sized for the initial 200 amp service, is now undersized for the upgraded 400 amp service. The local authority having jurisdiction, or OJ, might have initially allowed the smaller grounding electrode conductor, perhaps due to specific local interpretations or a lack of awareness regarding the future upgrades. However, using an undersized grounding electrode conductor poses several potential safety risks. Firstly, an undersized grounding electrode conductor might not be able to effectively handle fault currents. In the event of a ground fault, where a live wire accidentally comes into contact with a grounded metal part, a large amount of current flows through the grounding system. The grounding electrode conductor's job is to provide a low impedance path for this fault current to return to the source, allowing the circuit breaker to trip quickly and safely interrupt the power. If the grounding electrode conductor is too small, it might not be able to handle the fault current adequately, potentially leading to slower breaker tripping times, increased voltage on grounded metal parts, and a higher risk of electrical shock. Secondly, using an undersized grounding electrode conductor is a direct violation of NEC section 250.66. Electrical codes are in place to ensure safety and compliance, and violating these codes can lead to failed inspections, fines, and potential liability in the event of an electrical incident. To ensure compliance with the NEC and provide a safe electrical system, several steps should be taken. 1. Verify AHA requirements. Contact the local authority having jurisdiction to confirm whether they have any specific requirements or interpretations regarding grounding electrode conductor sizing for spec homes or situations involving service upgrades. They might have local amendments to the NEC or specific guidelines that need to be followed. 2. Upgrade the grounding electrode conductor if necessary. If the AHA requires compliance with NEC section 250.66, and the existing grounding electrode conductor is undersized for the upgraded service, it must be replaced with a conductor of the appropriate size. Consult NEC table 250.66 to determine the correct size of the grounding electrode conductor based on the size of the service entrance conductors. 3. Document all changes. Clearly document any changes made to the grounding system, including the size of the new grounding electrode conductor, the date of the upgrade, and any relevant inspection approvals. Provide this documentation to the AHA for their records. Additional considerations need to be taken into account. Upgraded services, as mentioned earlier, require a re-evaluation of the entire grounding system, not just the grounding electrode conductor. Ensure that all grounding connections are properly made and that the grounding electrode system is effective. Regular electrical inspections can help identify potential grounding issues and ensure that the system remains compliant with NEC requirements over time. Schedule periodic inspections by a qualified electrician to assess the condition of the grounding system and identify any necessary repairs or upgrades. In summary, when dealing with electrical service upgrades, especially in spec homes, it is crucial to prioritize safety and compliance with the NEC. Properly sizing the grounding electrode conductor according to NEC section 250.66 is essential for ensuring the effective operation of the grounding system and minimizing the risk of electrical hazards. Always consult with qualified electricians and local authorities to ensure that all electrical work is performed safely and in accordance with applicable codes and regulations. Now let's delve deeper into understanding the nuances of NEC Section 250.66 and its implications for grounding electrode conductor sizing. The NEC provides a comprehensive set of rules and guidelines for electrical installations, and Section 250 specifically addresses grounding and bonding requirements. Grounding is a critical aspect of electrical safety, as it provides a path for fault currents to flow back to the source, allowing overcurrent protection devices like circuit breakers to trip and to energize the circuit in the event of a fault. The grounding electrode conductor plays a vital role in this process, connecting the electrical system to the earth, which serves as a reference point for voltage stabilization and fault current dissipation. NEC Section 250.66 outlines the requirements for sizing the grounding electrode conductor based on the size of the service entrance conductors. The service entrance conductors are the wires that bring power from the utility company's transformer to the building's service equipment, typically the main service panel. The size of these conductors is determined by the overall electrical load of the building. NEC Table 250.66 provides a table that correlates the size of the service entrance conductors to the required size of the grounding electrode conductor. The table specifies the minimum size of the grounding electrode conductor for various service conductor sizes based on the material of the conductors, whether they are copper, aluminum, or copper-clad aluminum. It's important to note that the table provides minimum requirements, and in some cases, it may be necessary to use a larger grounding electrode conductor to ensure adequate grounding performance. Several factors can influence the selection of the appropriate grounding electrode conductor size. The type of grounding electrode used can affect the overall grounding impedance and the effectiveness of the grounding system. Common grounding electrodes include ground rods, concrete encased electrodes, and metal underground water pipes. The soil conditions in the area can also impact grounding impedance. Soil with high moisture content and high conductivity provides a better grounding path than dry, sandy soil. The length and depth of the grounding electrode can also affect its effectiveness. Longer and deeper electrodes generally provide lower grounding impedance. When upgrading an electrical service, it's essential to consider the existing grounding electrode system and determine whether it needs to be upgraded to meet the new load requirements. If the original grounding electrode was sized for a smaller service, it may not be adequate for the larger service, and a new grounding electrode may need to be installed. In some cases, it may be possible to supplement the existing grounding electrode with additional electrodes to improve grounding performance. When installing a new grounding electrode, it's important to follow the NEC requirements for electrode installation. Ground rods must be driven at least 8 feet into the ground and spaced at least 6 feet apart. Concrete encased electrodes must be encased in at least 2 inches of concrete and installed within the bottom 20 feet of a concrete foundation or footing. Metal underground water pipes can be used as grounding electrodes if they meet certain requirements, such as being electrically continuous and not having any insulating sections. In addition to the grounding electrode conductor, the equipment grounding conductors also play a crucial role in electrical safety. Equipment grounding conductors provide a low impedance path for fault currents to flow back to the source from metal enclosures of electrical equipment, such as appliances, lighting fixtures, and electrical panels. These conductors are typically run along with the circuit conductors and are connected to the grounding bus in the electrical panel. The equipment grounding conductors must be sized according to NEC Table 250.122, which correlates the size of the circuit conductors to the required size of the equipment grounding conductors. It's important to ensure that all equipment grounding conductors are properly connected and that there are no loose or corroded connections. Regular inspections of the grounding system can help identify any potential issues and ensure that the system is functioning properly. Now, let's address some common questions and concerns related to grounding electrode conductor sizing and electrical service upgrades. One common question is whether it's permissible to use a smaller grounding electrode conductor than required by NEC Table 250.66. The general answer is no. It's not permissible to use a smaller grounding electrode conductor than required by the NEC. The NEC provides minimum requirements for grounding electrode conductor sizing, and these requirements are based on safety considerations. Using a smaller conductor can compromise the effectiveness of the grounding system and increase the risk of electrical hazards. However, there are some limited exceptions to this rule. For example, NEC section 250.66 paragraph A states that if the grounding electrode conductor is connected to a concrete encased electrode or a ground ring, it does not need to be larger than number 4 copper or number 2 aluminum. This exception is based on the fact that concrete encased electrodes and ground rings typically provide very low grounding impedance, and a smaller conductor is sufficient to carry fault currents. Another common question is whether it's necessary to upgrade the grounding electrode conductor when upgrading an electrical service in an existing building. The answer is yes, it's generally necessary to upgrade the grounding electrode conductor when upgrading an electrical service. As mentioned earlier, the grounding electrode conductor must be sized based on the size of the service entrance conductors. If the service entrance conductors are increased in size to accommodate the increased electrical load, the grounding electrode conductor must also be increased in size accordingly. Failing to upgrade the grounding electrode conductor can result in an undersized conductor that is not capable of effectively handling fault currents. Another concern is the impact of ground faults on sensitive electronic equipment. Ground faults can generate voltage surges that can damage sensitive electronic equipment, such as computers, televisions, and audio equipment. To protect sensitive electronic equipment from ground fault surges, it's recommended to use surge protective devices, or SPDs. SPD are designed to divert surge currents away from sensitive equipment and protect them from damage. SPD should be installed at the service entrance and at branch circuits that serve sensitive electronic equipment. In addition to proper grounding and surge protection, it's also important to follow other electrical safety practices. Always use qualified electricians for electrical work and ensure that all electrical work is performed in accordance with applicable codes and regulations. Never overload electrical circuits and avoid using extension cords as permanent wiring. Regularly inspect electrical cords and appliances for damage and replace them if necessary. Install ground fault circuit interrupters, or GFCIs, in areas where there is a risk of electric shock, such as bathrooms, kitchens, and outdoor areas. GFCIs are designed to detect ground faults and quickly interrupt the power supply, preventing electric shock. By following these electrical safety practices, you can help protect yourself and your property from electrical hazards. And remember, when in doubt, always consult with a qualified electrician. Now let's consider some specific scenarios to further illustrate the principles of grounding electrode conductor sizing and electrical service upgrades. Scenario 1 involves a spec home with a 200 amp service that is later upgraded to a 400 amp service. The original grounding electrode conductor is number 6 copper, which is adequate for a 200 amp service. However, according to NEC table 250.66, a 400 amp service requires a number 2 copper grounding electrode conductor. Therefore, the grounding electrode conductor must be upgraded to number 2 copper to comply with the NEC. Scenario 2 involves an existing building with a 100 amp service that is being upgraded to a 200 amp service. The original grounding electrode conductor is number 8 copper, which is adequate for a 100 amp service. However, according to NEC table 250.66, a 200 amp service requires a number 6 copper grounding electrode conductor. Therefore, the grounding electrode conductor must be upgraded to number 6 copper to comply with the NEC. Scenario 3 involves a building with a concrete encased electrode that is being used as the grounding electrode. The service size is 400 amps. According to NEC section 250.66, paragraph A, the grounding electrode conductor does not need to be larger than number 4 copper when connected to a concrete encased electrode. Therefore, a number 4 copper grounding electrode conductor is sufficient for this application. Scenario 4 involves a building with a ground rod that is being used as the grounding electrode. The server size is 200 amps. According to NEC Table 250.66, a 200 amp service requires a number 6 copper grounding electrode conductor. The ground rod must be driven at least 8 feet into the ground and spaced at least 6 feet apart from any other ground rods. In addition to the above scenarios, it's also important to consider the specific requirements of the local authority having jurisdiction, or OJ. The AHJ may have local amendments to the NEC or specific guidelines that need to be followed. Always consult with the AHJ to ensure that all electrical work is performed in accordance with applicable codes and regulations. Electrical inspections are an important part of ensuring electrical safety and compliance. Regular electrical inspections can help identify potential grounding issues and other electrical hazards. Schedule periodic inspections by a qualified electrician to assess the condition of the electrical system and identify any necessary repairs or upgrades. Electrical inspections can also help ensure that the electrical system is properly maintained and that all electrical equipment is functioning properly. In summary, understanding the principles of grounding electrode conductor sizing and electrical service upgrades is essential for ensuring electrical safety and compliance. Properly sizing the grounding electrode conductor according to NEC Section 250.66 is crucial for ensuring the effective operation of the grounding system and minimizing the risk of electrical hazards. Always consult with qualified electricians and local authorities to ensure that all electrical work is performed safely and in accordance with applicable codes and regulations. Now let's broaden our discussion to include other aspects of electrical grounding and bonding that are closely related to the sizing of the grounding electrode conductor. Grounding and bonding are two distinct but interconnected concepts in electrical safety. Grounding refers to connecting the electrical system to the earth, while bonding refers to connecting different metal parts of the electrical system together to create a low impedance path for fault currents. Both grounding and bonding are essential for preventing electric shock and minimizing the risk of electrical hazards. The grounding electrode conductor, as we have discussed, connects the electrical system to the earth. The equipment grounding conductors connect the metal enclosures of electrical equipment to the grounding bus in the electrical panel. Bonding jumpers are used to connect different metal parts of the electrical system together, such as metal conduits, metal enclosures, and metal water pipes. The purpose of bonding is to create a low impedance path for fault currents to flow back to the source. If a fault occurs and a live wire comes into contact with a metal part, the fault current will flow through the bonding jumpers and equipment grounding conductors back to the grounding bus in the electrical panel. This will cause the circuit breaker to trip and energize the circuit, preventing electric shock. The size of the bonding jumpers is determined by NEC Table 250.102, which correlates the size of the service entrance conductors to the required size of the bonding jumpers. It's important to ensure that all bonding jumpers are properly connected and that there are no loose or corroded connections. Another important aspect of grounding and bonding is the concept of a separately derived system. A separately derived system is an electrical power source, such as a generator or a transformer, that is not directly connected to the utility company's electrical grid. Separately derived systems require their own grounding electrode system. The grounding electrode conductor for a separately derived system must be sized according to NEC Section 250.30. The size of the grounding electrode conductor depends on the size of the derived phase conductors. In addition to the grounding electrode conductor, separately derived systems also require a bonding jumper to connect the neutral conductor to the equipment grounding bus. The size of the bonding jumper is determined by NEC Section 250.28. Surge protection is another important aspect of electrical safety that is closely related to grounding and bonding. Surge protective devices, or SPDs, are designed to protect electrical equipment from voltage surges caused by lightning, power line disturbances, or switching events. SPD work by diverting surge currents away from sensitive equipment and protecting them from damage. SPD should be installed at the service entrance and at branch circuits that serve sensitive electronic equipment. The effectiveness of SPD depends on proper grounding and bonding. SPD must be properly grounded to provide a low impedance path for surge currents to flow back to the source. The grounding electrode conductor and the equipment grounding conductors must be properly sized and installed to ensure that SPD function effectively. In summary, grounding and bonding are essential for electrical safety. The grounding electrode conductor, equipment grounding conductors, and bonding jumpers all play crucial roles in preventing electric shock and minimizing the risk of electrical hazards. Separately derived systems require their own grounding electrode system. Surge protective devices can protect electrical equipment from voltage surges, but their effectiveness depends on proper grounding and bonding. Always consult with qualified electricians and local authorities to ensure that all electrical work is performed safely and in accordance with applicable codes and regulations.